Welcome to the second lecture on backtracking. In the first lecture on backtracking, we have seen the principle of backtracking, state space tree, how backtracking explores the state space tree for possible solutions, and we have seen how n-Queen's problem can be solved. Of course, subsequently, we also saw how n-Queen's problem can be coded. Now, in this lecture, we will see how to solve the sum of the subsets problem, making use of backtracking. The statement of the sum of subsets problem goes like this. You are given n positive integers. Often these integers are also called as weights. So you are given n weights, wi, 1 less than or equal to I less than or equal to n, and an integer m, so that you find all the subsets of wi which sum to m. Of course, there is a fundamental property to be satisfied by the given problem. If you sum up all the weights, it should be greater than or equal to m. Otherwise, you will not be able to find a solution to the given problem. Now, let's look at an example. We are given 4 weights. The weights are 7, 11, 13, and 24. And the value of m equal to 31. So what are the possible solutions to this problem? If you recollect, in the first lecture we said the solution often can be expressed in the form of a variable size tuple or fixed size tuple. In fact, in this problem, it's possible that the solution can be expressed in either way. Let's look at the variable size tuple representation. The solution to this problem is 1, 2, 3, which says that the first, second, and third weights as a subset will sum up to 31 and qualify to be the solution of the problem. In fact, the first, second, and third weights are 7, 11, and 13, and the sum is 31. So it satisfies the given statement of the problem and happens to be one of the solutions. We also have another solution, and the solution is represented as 1 and 4, which means that the first weight and the fourth weight as a subset satisfy the solution of the problem. In fact, the first weight is 7 and the last weight is 24. The sum happens to be 31. So this is the way we express the solution as a variable size tuple. Let's look at how can we express the solution as a fixed size tuple. In the fixed size tuple, the number of components in the tuple is fixed. Now in this example, we were given 4 weights. So the solution always happens to be a 4 tuple. So two possible solutions for this problem are 1, 1, 1, 0, which means that the first 3 weights are included and the fourth weight is excluded. And the second solution says 1, 0, 0, 1, which means that the first weight is included and the fourth weight is included, but second and third weights are excluded. Now in this lecture, we follow fixed tuple representation. Of course, as I said earlier, the problem statement shall always satisfy that sum of all the weights given should be greater than or equal to m, without which the solution for the problem does not exist. Now, in backtracking, the nucleus of the methodology is the state space tree. So how should we envisage the state space tree in the sum of subsets problem? One possible way to design the state space tree is at any node level k, at any node which is at level k, we create the children by choosing the values of xk equal to 1 and xk equal to 0, which indicate that the kth weight is included in the solution or the kth weight is not included in the solution. As a result, we find that the state space tree is a binary tree. Now let's look at how does the state space tree look like. As I said, this is the conceptualization of the state space tree. This state space tree is never constructed in its complete sense. This is the root node at which we begin and which is at level k equal to 1. So at k equal to 1, we choose the values x1 equal to 1 and x1 equal to 0. So x1 equal to 1 defines a node, and this node indicates the partial solution where weight 1 is included. And by choosing x1 equal to 0, we create a node which indicates the partial solution where the first weight is not included, which means in the solution tuple, the first value will be 0 here. Whereas in the solution tuple, the first value here will be 1. And now let's look at this node. Now at this level, k equal to 2, we create children by choosing the value of x2 equal to 1 and x2 equal to 0. So this node defines a partial solution x1 equal to 1, x2 equal to 1. So the partial solution is 1 comma 1 at this solution, which indicates that the first weight and the second weight are included. Whereas this node indicates the partial solution 1 comma 0, which means that the first weight is included but the second weight is excluded. So this is how the state space tree grows, and let's look at a few more examples. This node represents the partial solution 0, 1, 0, which means the first weight is not included, second weight is included, and the third weight is not included. And finally, if you look at leaf nodes, this leaf node represents the solution 1, 0, 1, 1, which means the first weight is included, second weight is not included, third weight is included, and the fourth weight is included. Now, one more aspect of this state space tree is that any node can be a solution node. You have to note that any node can be a solution node. For example, this node, which represents the partial solution 1, 0, 1, which means that the first weight is included, second weight is not included, and the third weight is included, may represent a solution, which means that the first weight and the third weight included will result in a value which is equal to m, and hence this represents the solution. And of course, the obvious question is what would be the fourth value? The fourth value here would be equal to 0 because the first and third weights itself would sum up to the value equal to m. So we realize that in contrast to the n-queens problem, where leaf nodes represents the solution nodes, here all the interior nodes represent the solution nodes. Of course, all of them may not be the answer nodes, but some of them may be the answer nodes. So this is one more flavor what we normally encounter in backtracking. Solution nodes can be interior nodes, or the solution nodes can be the leaf nodes. In some problems, the solution nodes can only be the leaf nodes, or in the other way around, leaf nodes only can only be the solution nodes. Now, with this backdrop of state space tree, let's look at the partial solutions represented by the sum of the nodes. This represents the partial solution 1. This represents the partial solution 1, 0, 1. This represents the partial solution 0, 0, 1. And as I said, if this node happens to be the answer node, then obviously we will take the last one as 0. So the solution will be, the answer will become 1 0 1, provided 1 0 1 0, provided this node is the answer node. Now, each node in the state space tree, as we discussed earlier, represents a partial solution x1, x2, xk. In the figure, Q is a child of P and it represents the partial solution x1 equal to 1 and x2 equal to 0. So far we have seen how the state space tree can be envisaged for solving the sum of subsets problem. But one more important aspect of applying backtracking is being able to find out the bounding function. So what is the bounding function in the sum of subsets problem? Let's take a typical scenario while constructing the state space tree. We assume that we started at the root node. We have chosen a value of x1 equal to 1, as a result of which this node is created. And then we have chosen x2 equal to 0, as a result of which this node is created. And we are at level k equal to 3. And now we have to choose, according to our solution strategy, xk, that is x3 equal to 1 or x3 equal to 0, and create the children corresponding to the values of xk, that is x3. Let's choose x3 equal to 1 and create this child. So this child represents the partial solution 1, 0, 1. Now after creating the child corresponding to x3 equal to 1, what should be tested about this partial solution? Or in other words, what is the bounding function to be applied to this partial solution so that we make a decision of whether this node needs to be killed, or you can make this node as the E node and then proceed to create its children. I repeat, once this node is created, it defines a partial solution and we have to apply a bounding function so that you can find out the partial solution, whether it promises a solution and hence we can make this node is an E node, or we have to kill this node because this node no more can promise a solution. So in that spirit, what should be the bounding function? One obvious thing is the sum of the weights included as defined by this partial solution should be less than or equal to m. That is, if you take this example, x1 equal to 1, x2 equal to 0, and x3 equal to 1. The first weight is included, the second weight is excluded, and the third weight is included. So the sum of the first weight and the third weight should be less than or equal to m. If it is less than m, then we hope that we can proceed further, and probably at a next level we shall be able to find a solution. Suppose if it is equal to m, then we start our exploration here itself because we found out a solution. So this can be expressed mathematically as, at the newly created node, the sum of the weights included should be less than or equal to m. So it says that sigma I equal to 1 to k, because the partial solution is x1, x2, xk. So I equal to 1 to k, xi wi should be less than or equal to m. Of course, if the sum is equal to m, then it is the answer node. Sigma I equal to 1 to k, xi wi equal to m says that this is the answer node. If it is less than m, then we hope that we explore further and we'll be able to find out some combination of weights so that this sum will be equal to m. Of course, this partial solution should satisfy another condition also. The condition is, suppose if the sum of the weights included so far is less than m, then one should be ensured that the sum of the weights included so far and the sum of the remaining weights should be greater than or equal to m. And if it is not greater than or equal to m, we will not be able to find a solution because the remaining weights included with the existing sum will not guarantee a minimum weight of m. And we want to achieve a minimum weight of m as a solution to this problem. So hence, the second solution to be satisfied, rather the second condition to be satisfied by this partial solution, x1, x2, xk is sigma equal to 1 to k xi wi, which means that some of the weights included so far, plus sigma equal to k plus 1 to n xi wi. It is sum of the remaining weights. If both these sums put together should be greater than or equal to m, so that we hope for a solution, if not now, at a later point of time as we explore the state space tree. Let's try to find some simplification. The first part of the sum let's try to find some simplification. This first part of the weight, sigma is equal to 1 to k xi wi, which represents the weights included, some of the weights included as defined by this partial solution as S. Let's call it as S. S is the sum of the weights chosen so far. Similarly, let's call this part of the sum, which is the sum of the weights remaining, as R. So R represents the sum of the weights remaining and yet to be considered, which are from Wk plus 1 to Wn. As a result, the conditions to be satisfied by the partial solution can be expressed in simple terms as S should be less than or equal to M. Of course, if S is equal to M, then it becomes the answer node. And the second condition to be satisfied by the partial solution is S plus R should be greater than or equal to M. So this is a simplified representation of the bounding function and the conditions to be satisfied. Now, why did we choose this notation of S and R? Let's see. We can easily find out that by this notation of S and R, we can very easily calculate the values of S and R. I've written M here. This is not M. This is R. S and R can be very easily computed. Suppose we have started at the root node. At the root node, what are the values of S and R? At the root node, we haven't chosen any weights. So the sum of the weights included should be equal to 0 because the root node does not define any partial solution. It's a null solution at the root node. So the value of S equal to 0. What is the value of R? All the weights are remaining because no weight has been considered yet. So the value of R equal to sigma I equal to 1 to n wi. That is the sum of all the weights given in the statement of the problem. Now let's see what will be the values of S and R at the node defined by x1 equal to 1. So at the child defined by x1 equal to 1, S will be incremented by W1. Previously S equal to 0. So here S will be 0 plus W1, the previous sum plus the weight that has been considered, that is W1. And because W1 is considered, R will be decremented by W1. So we find that with respect to the parent, S and R values can be very easily computed. If you know the value of S and R at the parent, at the node defined by x1 equal to 1. Please note, this discussion is valid only at the node defined by x1 equal to 1. So at the node defined by x1 equal to 1, S will be incremented by W1, R will be decremented by W1. I think it can be generalized now that if you know the values of S and R at any level k, then in the next level S will be incremented by Wk and R will be decremented by Wk at the node defined by xk equal to 1. But the story is different at the node defined by xk equal to 0. At the node defined by xk is equal to 0, we know that Wk is not considered, and hence if you take the root node, for example, at the child node defined by x1 equal to 1, the sum remains to be constant because you haven't considered the weight w1. And because you haven't considered the weight w1, r will be decremented by w1. So we generalize now once again. At any level k, if you have the values of s and r, at its child defined by xk equal to 0, s will remain to be the same, but r will be decremented by wk. So this is a beautiful observation and it helps us in easily calculating the values of s and r at the children, know the values of s and r at the parent. That's the reason why we have adopted the simplified notation S and R, and we also have expressed the bounding function in terms of S and R. Let's make one more final elegant observation. If this bounding function is to be satisfied by this node, then one should accept that this bounding function should have been already satisfied by the parent node. If the bounding function was not satisfied by the parent node, we wouldn't have considered this as E node and wouldn't have constructed the children. So the bounding function obviously should have been satisfied by the parent as well. Now let's try to write the bounding function at the parent, which is already satisfied. How does the bounding function look like? S dash should be less than or equal to M, because at the parent probably the sum of the weights chosen is S dash. And the sum of the remaining weights probably is r dash. So the bounding function might have been satisfied. S dash plus r dash is greater than or equal to M. But we know that with respect to the node xk equal to 1, there is a definite relationship between S prime and S. What is the relationship between S prime and S? We know that S is equal to S prime plus Wk. S is equal to S prime plus Wk. Hence S prime is S minus Wk. So you can rewrite this as S minus Wk should be less than or equal to M. Similarly, the other condition, S prime plus R prime should be greater than or equal to M. There is a definite relationship between R prime and R. What is the relationship between R prime and R? R is equal to R prime minus Wk. This R is R prime minus Wk because R will be decremented by Wk. So R prime is R plus Wk. Hence, this condition becomes S minus Wk plus R plus Wk should be greater than or equal to M. So if Wk and minus Wk get cancelled, we find that S plus R is greater than or equal to M. So if S plus R is greater than or equal to M at the parent node itself, there is no need to check for this condition at the child node defined by xk equal to 1. Please remember that all this discussion is valid only at the node defined by xk equal to 1. So at the node xk defined by xk equal to 1, though the bounding function demands for two conditions to be satisfied, the second condition is automatically satisfied because the second condition is automatically satisfied at the parent itself. So that's the reason why we don't need to check this condition as a part of the bounding function, and the bounding function is very simple. S should be less than or equal to M. If S is less than or equal to M, then we make this as E naught. And we also know that S can be very easily calculated. We have to add only weight Wk to the sum at the parent node. You automatically get the value of S, and that value of S should be less than or equal to M if this node were to be made as the E node. Otherwise, we kill this node. Of course, you can also understand the Of course, you can also understand why this condition need not be checked at the node defined by xk equal to 1. Now, at the parent node, let's suppose we have weights w1, w2, wk minus 1 are added, and that is represented by S. And weights wk and wk plus 1, wn minus 1, w1 are added, that represents the r value at the parent node. Now, what happens at the child node? At the child node, this wk moves from r to s. So that s will be incremented by wk, r will be decremented by wk. So we find that the total remains to be the same, only wk gets shifted from r to s, and hence the value of s plus r does not change, and hence there is no need to check for the condition s plus r greater than or equal to m at the child node, because it is already satisfied at the parent node. So now we conclude that at the child node defined by xk equal to 1, the bounding function demands for only one condition to be satisfied, and that condition is the sum of the weights included at that node should be less than or equal to m. And of course, if the sum equal to m, we will announce that to be an answer node, and we backtrack or we explore the remaining part of the state space tree. Now let's try to develop the bounding function at the node defined by xk equal to 0. Let's see. So the bounding function once again requires in its primitive mode that the two conditions are to be satisfied. S should be less than or equal to m. S plus r should be greater than or equal to m. Now, as we have seen in the previous node, let's try to find the relationship between the conditions to be satisfied at the parent node and at the child node defined by xk equal to 0 this time. So this defines the partial solution for the example 1, 0, 0. Okay. Now let's see. The condition to be satisfied here is S prime should be less than or equal to M. And S prime plus R prime should be greater than or equal to M. Now what's the relationship between S prime and S, where we are talking about S and R at the node defined by xk equal to 0. That's more important. We know that because the node is defined by xk equal to 0, wk is not included. So S prime and S are one and the same. They are one and the same. And because the weight wk is not included, we know that this r prime gets decremented by w, and r equal to r prime minus wk. So the newly written conditions will be S is less than or equal to m, because there is no difference between S prime and S because wk is not added. And the second condition becomes S plus R plus wk should be greater than or equal to m. And we find that S less than or equal to m is already satisfied at the parent, and hence it need not be checked at the node corresponding to xk equal to 0. So we find a new flavor of bounding function. In N-Queen's problem, the bounding function is common, which is to be satisfied at each and every node. But here, the bounding function appears in two forms. At the node defined by xk equal to 1, you need to check only S is less than or equal to m. At the node defined by xk equal to 0, you need to check whether s plus r is greater than or equal to m. If the bounding function is satisfied, you will make it as E node and explore further in the state space tree. If the bounding function is not satisfied, we kill those nodes and either we look at the next alternative value of the xk or we backtrack and then explore the remaining part of the state space tree. And as we have seen in the earlier mathematical formulations, to avoid summation of weights and each node, we maintain in the state space tree a three-tuple skr associated with each node. K is the level of the node. Of course, S is the sum of the weights included as defined by the partial solution at that node and at the root node S equal to 0. And R is the sum of the remaining weights to be considered in building the solution. And at the root node R is the sum of all the weights. So if you look at probably this graphic, all things should be made clear. At this node, the three tuple is skr. Now this node has two children defined by xk equal to 1 and xk equal to 0. At the child defined by xk equal to 1, s becomes s plus wk, r becomes r minus wk. And of course, the level is incremented by 1. At the node defined by sk equal to 0, s remains to be the same because you are not including wk in the solution. And r becomes r minus wk because you are excluding wk, you are not including wk, it's no more being considered. So some of the remaining weights get decremented by wk, and of course the level will be incremented by k plus 1. And let's summarize now and try to formalize the bounding function. Any node defined by x1, x2, xk is an answer node if s is equal to m. Some of the weights included so far as defined by the partial solution. That is, sigma I is equal to 1 to k xi wi. If it is equal to m, then it is an answer node. Otherwise, you apply the bounding function v of x1, x2, xk. It returns true if s is less than or equal to m at the node xk equal to 1. So the bounding function only looks for whether s is less than or equal to m at the node defined by xk equal to 1. And at the node defined by xk equal to 0, the bounding function looks only for the condition s plus r is greater than or equal to m. So we should remember that xk equal to 1 and xk equal to 0 call for different bounding functions, which is the beauty of sum of subsets. So this is the condition to be satisfied at the node defined by xk equal to 1, and this is the condition to be satisfied at the node defined by xk equal to 0. Now with this backdrop, let us proceed to solve the problem n is equal to 4, w1, w2, w3, w4 equal to 7, 11, 13 and 24, and m is 31. As we saw earlier, we started the root node, which is at level k equal to 1. And we also said that at each node we maintain a three tuple s, k, r. K represents the level 1 because we are at the root node, and s is 0 because we haven't yet considered any weight. So some of the weights included so far by the partial solution is 0 because there is no partial solution at the root node. And of course, r is the remaining sum of the remaining weights, and all are the remaining weights. None of them have been considered yet. So sum of all these four weights is 7 plus 11, 18. 18 plus 13 is 31, and 24 plus 24 is 55. So we start with this. And now, because we are at level k, we knew in backtracking we have a standard step of creating the children by choosing the value of xk. Now, what are the values of xk? That is x1, in our state space tree corresponding to the sum of subsets problem. We said the values xk can take on are 1 and 0. Xk equal to 1 indicates that the weight wk is included, and xk equal to 0 indicates that the weight wk is not included or excluded in the solution. So let's start with xk equal to 1. Because k equal to 1, x1 equal to 1, which means that the partial solution contains weight 1. So if the partial solution contains weight 1, this is the node created. And we knew at the node x1, xk equal to 1, S will be incremented by wk, R will be decremented by wk. That's what we have observed in our previous formulation. So weight 1 is 7. So this sum will be incremented by 7 and this R will be decremented by 7. So it becomes 7, 2 and 48 because we have reached to the next level, the level value k equal to 2. Now what is the bounding function to be applied here? The bounding function to be applied here is s less than or equal to m or not. So 7 is less than or equal to 31. Yes or no? Yes. So the bounding function returns a value of true. So this becomes the next E node and then we create its child. How do we create its child? We create its child by choosing a value of x2 equal to 1 because this node is at level 2. So the bounding function is satisfied. So we make it as E node and then we create the child of this E node by choosing value of x2 equal to 1. What does it mean to say x2 equal to 1? Means w2 is considered. So at the node defined by x2 equal to 1, s will be incremented by w2, r will be decremented by w2. What is w2? 11. So 7 will be incremented by 11, so it becomes 18. 48 will be decremented by 11, and hence it is 37. So this is the newly created child. It defines a partial solution. What is the partial solution defined? 1, comma 1. x1 equal to 1, x2 equal to 1. This node is the result of choosing x1 equal to 1 and x2 equal to 1. Now, does it satisfy the bounding function? The bounding function to be satisfied at the node corresponding to xk equal to 1 for any k is whether s is less than or equal to m. 18 is less than or equal to 31. True. So this becomes the E node and once again we create its child. How do we create its child? By choosing a value of x3 equal to 1. So x3 equal to 1 defines a partial solution where w3 is included in the solution. What is w3? 13. So 18 will be incremented by 13, that is it becomes 31, and 37 is decremented by 13, that is 24. S and R values are very easily calculated by using this notation. And now, because this is now the child created, let's apply the bounding function. Whether s is less than or equal to m, we find that s is equal to m. So if s is equal to m, we have reached an answer node. So we find that this is an answer node. And what is the solution? The partial solution created so far is 1, comma 1, comma 1. And because this node became an answer node, there is no need to consider the remaining weights. So the remaining weight is x4. So we give a value of x4 equal to 0 for it. And hence the partial solution is 1, comma 1, comma 0. Of course, we don't stop here. We try to explore for all possible solutions. So to explore for all possible solutions, what we do is we go to the parent and try to create the child corresponding to x3 equal to 0. So x3 equal to 0, we know that the values of s and r are calculated as s remains to be the same as that of the parent node. So 18 remains to be 18, the value of s, and 37 will be decremented by w3. w3 is 13. So because we are not considering w3, x3 equal to 0 says that the w3 is not going to be considered. So 37 is decremented by 13 and hence it becomes 24. And now what is the bounding function to be applied here? At the node corresponding to xk equal to 0, we found out that the bounding function to be satisfied is s plus r should be greater than or equal to m, so that there is a hope of getting solution somewhere. So 18 plus 24 is greater than 31, and hence this becomes the E node, and we create the child for it. S plus R greater than or equal to M. 18 plus 24 is greater than or equal to 31 is satisfied, and hence we create its child. Which child is created? The child corresponding to x4 equal to 1 is created first. And at the child defined by x4 equal to 1, S will be incremented by W4. W4 is 24. So 18 plus 24 is 42. R will be decremented by W4. 24 will be decremented by 24, and hence R will become 0. So here the sum is 42 and S is 42 and R is 0. Now, does it satisfy the bounding function? The bounding function says is S less than or equal to M. If S is equal to M, this purports to be an answer node. Is S equal to M? S is not equal to M. In fact, S is greater than M, and hence this node is killed. Of course, we also should remember that we have reached a level n greater than 4. We have reached a level greater than n, that is greater than 4. We have reached a level 5. When we have reached level 5, we don't further expand the state space tree because the nodes at level 5, because n is equal to 4, define the leaf nodes. So we stop here. We don't expand this as the E node because this has reached, this node is created at level n plus 1, and we move on to x4 equal to 0 to create the next child. X4 equal to 0. This node, of course, has the values of S and R are calculated as S remains as S, so 18 remains as 18. And 24 is decremented by W4. W4 is 24, so 24 is decremented by 24, it becomes 0. And at the node defined by xk equal to 0, the bounding function is S plus R should be greater than or equal to M, whether S plus R is greater than or equal to M. However, we don't need to check for this bounding function because, as I said, this node is at level 5. The value of n equal to 4, and hence we don't expand the nodes at level 5 because level 5, that is n plus 1, is the last level which we reach in our state space tree. So we no more need to expand. So it's trivial to test for the bounding function here. So once we have concluded this node need not be expanded further, we go back to the parent. The parent has been expanded. It becomes a dead node because all of its children have been generated. Then we go to its parent. All of its children have been generated. Then we go back its parent. Of course, there is one child pending to be generated, and hence we create the child of this node corresponding to x2 equal to 0. Now x2 equal to 0 results in this child, and the value of s remains to be the value of s at the parent, and the value of r will be decremented by w2. 48 will be decremented by 11, and hence it becomes 37. Now what is the bounding function that has to be applied at a child defined by xk equal to 0? The bounding function is s plus r should be greater than or equal to m. And we know that 7 plus 37 is greater than or equal to 31. So this becomes an E node. And once again, we create its child by choosing x3 equal to 1 first. Because we have chosen x3 equal to 1 at this node, S will be incremented by W3, 7 will be incremented by 13, and hence it becomes 20 here. And the 37 will be decremented by 13, so R will become 24. And because this is a node defined by xk equal to 1, you have to check whether s is less than or equal to m. So the bounding function to be tested is s less than or equal to m, 20 is less than or equal to 31. So once again, we make this node as the E node, and create its child corresponding to x4 equal to 1. Because it's a child corresponding to x4 equal to 1, the value of s will be the value of s at the parent plus w4. W4 is 24. So 20 plus 24, it becomes 44. And r will be decremented by w4, that is 24 becomes 0. And now, shall we apply the bounding function here? The bounding function to be applied is s less than or equal to m. Of course, s is greater than m here. So we kill this node. We don't go further. Even otherwise, if it is not an answer node, we do not go further because this node is at level 5, at level n plus 1, because the value of n is 4 in this problem. And then we create the child x4 equal to 0. The value of s and r will be 20 and 0, because w4 is 24, s remains to be the same 20, and r will be decremented by 24, and hence it becomes 0. And at this node, we need not check for any bounding function, because this node is at level 5, we no more expand. So because this becomes a dead node now, all of its children have been generated, we go back and look at the child x3 equal to 0. So at x3 equal to 0, sum remains to be the same, 7. The level will incremented by 4, and 37 will be decremented by w3. w3 is 13, so it will be decremented by 24. And now what is the bounding function to be applied? Because this is the node corresponding to xk equal to 0, the bounding function is s plus r should be greater than or equal to m, and 24 plus 7 is greater than or equal to 31, and hence we expand this. This becomes the e node. We expand this with x4 equal to 1, and x4 is equal to 24. So s will be incremented. W4 is 24. So 7 plus 24, s becomes 31, and r becomes r minus 24. That is 24 minus 24, 0, and we reach the level 5. And at level 5, we only check whether s is equal to m or not, and we find that s is equal to m, and hence this is an answer node. So we find that we reached both the answer nodes. In fact, there are no more answer nodes, but still, I encourage you to complete the remaining part of the state space tree and get a feel of how the nodes are created and how the nodes are killed. With this, we complete a second application of backtracking algorithm. I hope this application further might have substantiated your knowledge on application of backtracking to certain classes of problems where the solution space is very large and problems are likely to have more than one solution. I have listed here two problems, one with n equal to 4 and another with n equal to 5. You can solve these problems by drawing the state space tree and exploring all possible solutions of these two problems. So that brings us to the end of the lecture. Thank you.